So in this lecture, I will discuss bounded linear functionals on Hilbert spaces. And so just a remark or an observation. Let me start with an observation. So let me fix x in a Hilbert space X. And let me define L of x in R or in C, so in the field K, as L of y equal to the scalar product of y with x. And what I claim is that L, it's a bounded linear functional. That L is linear, it's clear. I leave it to you to check. And that L, it's bounded, well, if you take L of y, the absolute value of that, it's the absolute value of the scalar product. And this, by Schwarz inequality, it's bounded by the norm of y times the norm of x. And so we get that indeed L, it's a bounded linear functional, and moreover, that the norm of L, it's bounded by the norm of x. So we have, in this way, for each element x, a linear functional. Maybe I should represent this linear functional by L of x. And what we proved is that the norm of this linear functional, it's bounded by x, and this is due to Schwarz inequality. Well, one of the main theorems of this lecture is that whatever the bounded linear functional you have on a Hilbert space X, it's given by this expression. More precisely, so if X, it's a Hilbert space, and if L, it's a bounded linear functional from X to K, so it's a bounded linear functional, what I claim is that then there exists x in x such that L of y, it's equal to y, the scalar product of y with x. And this is called Ris Representation Theorem. And this is the first main result of this lecture, so that we have all bounded linear functional can be represented as scalar product with respect to a fixed element x. To prove this theorem, we will start with a lemma, and then we'll go to the proof of the theorem. So here's the lemma. Again, we have x, a Hilbert space. And let's say, let L be a bounded linear functional on x. And let me define the null space of L and L as all points x in x such that L of x is equal to 0. And the claim is that NL has codimension 1, which means that x can be written, well, if, and I'm assuming that L is different from 0. Of course, if L is equal to 0, the null space is the old space, so let's assume that L is different from 0, and what I claim is that x, it's equal to a space of dimension 1. So the space generated by an element W plus n, L. So has codimension 1. This means that there exists W in x such that x can be written as a scalar multiplying W plus an element of NL. And then my second statement is that suppose that you have L and M bounded linear functionals, and suppose that the null space coincides. So NL is equal to NN. Well, in this case, what I claim is that then there exists a constant C, a scalar C, such that L is equal to C times N. So we will prove these two lemmas in the next few minutes. So let's prove the first claim. So I'm assuming that L is different from 0, which means that there exists a W in X such that L of W is different from 0. We proved already this lemma in the context of Banach spaces, but let me prove it here again. So now I want to write any element of X as a scalar multiple of W plus an element of the null space. So consider an element X in X. And, well, what we will do is we'll define, since LW is different from 0, I can always divide it by LW, multiply that by LW, because, well, if I have to represent X as a scalar multiple of W plus an element in the null space, if I apply L, so if I have this identity, by applying L on both sides, on the left-hand side I get Lx. This is an element of the null space, so L of n is equal to 0, so that disappears. And here, by linearity, I get this scalar times L of W. So this scalar has to be equal to L of x divided by L of W, because they will cancel, and the left-hand side is equal to L of x. So this has to be the scalar which is multiplying W. And then, well, for the element in the null space, I will just write that as x minus Lx divided by Lw. Well, the identity, it's obvious because this term will cancel this term. So the only thing I need really to care is to show that this expression is an element of the null space. But if you apply L to this element, by linearity you get Lx minus Lx divided by Lw of Lw. The Lw cancels with the L of W, and I get Lx minus Lx. So this indeed is an element of the null space of L. And therefore, I wrote X as a scalar multiple of W plus an element of the null space. So I can always write an element of X as a sum of elements of these two spaces. Now let me check that the intersection of these two spaces is empty. So I have to prove that the intersection of these two spaces, it's not empty, as I said, but it's equal to the 0 element. So let's take an element Z in this intersection. And let's show that Z has to be equal to 0. So on one hand, Z is equal to alpha W for some alpha in K, because Z it's an element of this space. On the other hand, I know that Z it's an element of the null space, so L of Z it's equal to 0. So since L of Z is equal to 0, I apply L on both sides of this identity, and by linearity what I get is that L of Z it's equal to alpha times L of W. Well, L of W is different from 0. L of Z it's equal to 0 because Z belongs to the null space, and this implies that alpha has to be equal to 0, and therefore that Z is equal to 0. This proves that the intersection is indeed composed of only the 0 element and completes the proof of the first claim. So here is the second statement we want to prove. If we have two bounded linear functionals, L and M, whose null space coincide, we want to prove that one is a multiple of the other. So there exists a scalar C such that L is equal to Cm. So first, let's consider the case in which L is equal to 0. This case is trivial because if L is equal to 0, this implies that the null space of L is the whole space, but the null space of L coincides with the null space of M. So this tells you that the null space of M is equal to X. And if the null space of M is equal to S, this means that M is equal to 0. So both are 0, and that identity holds trivially. So I can always assume that L is different from 0. So let's assume that L is different from 0. And let's recall the proof of the first claim of this lemma is that then there exists, well, since L is different from 0, there exists a W in X such that L of W is different from 0. And moreover, that X can be written as the space spanned by W plus the null space of L. But the null space of L coincides with the null space of M by assumption. And also, L of W being different from 0, this implies that M of W is different from 0. Because if M of W were equal to 0, W would be an element of the null space of M, which coincides with the null space of L, and therefore L of W would be equal to 0. So since it's different from 0, we have that M of W is different from 0. Now I want to show that L is a multiple of M. So let's consider a point X in X. Well, since all the elements of X can be written as a sum of an element in this space and an element of that space, X, it's equal to alpha times omega plus n, where n belongs to the null space of L, which is also the null space of M. And alpha, it's a scalar. So if I compute L of X, and I want to show that L of X is a multiple of M of X, well, by this expression, I get that this is by linearity alpha times L of W, and L of n is 0 because n is an element of the null space. Well, since M of W is different from 0, I can multiply that and divide that by M of W. And now, by linearity, I can introduce alpha inside M and add n. So what I claim is that this is equal to L of W, M of W times M alpha W plus n. Well, because M of n is 0, because n belongs to the null space of M. And here, by linearity, I can remove, I can take out alpha from M. But X, it's exactly equal to alpha omega or W plus n. So this is L of W divided by M of W times M of X. And since X, it's a general element of X, we just proved that L of X, it's equal to this quantity multiplying M of X. So here is our scalar C, which appears in the assertion of this lemma. So here is a third property that we'll need in the proof of the theorem. I take again L, a bounded linear functional on a Hilbert space X, and what I claim is that the null space N of L is closed. And the proof, it's very simple. So let's take xn in the null space, xn converging to x, and we want to show that x belongs to the null space. So for that, we need to prove that L of x is equal to 0, but L of x, since xn converge to x, I claim that this is equal to the limit of L of xn, and that's clear because if you take L of xn minus L of x, this is equal to, by linearity, L of xn minus x, and this is bounded because by definition of the norm of L, this is bounded by the norm of L times the norm of xn minus x, and the norm of xn minus x is converging to 0 because xn is converging to x. This norm is finite because L is a bounded linear functional, and this proves that indeed L of x is equal to L of xn. But since xn belongs to the null space, this sequence is a sequence which is constant equal to 0, and therefore L of x is equal to 0, which shows that indeed the null space of a bounded linear functional is closed. So I rewrote the theorem which I want to prove. We have a Hilbert space, a bounded linear functional L, and I want to show that this bounded linear function L can be represented this way, so that there exists an element x in X, such that L of y is equal to yx, the scalar product of y and x, for all y in X. So let's prove that. I first observe that I can always assume that L is different from 0, because if L is equal to 0, then I can just take x equal to 0, and we have this identity, so there is nothing to prove. So I can assume that L is different from 0. Now, if L is different from 0, we have seen that there exists a W in X such that L of W is different from 0, and that the space X can be represented by the span of W plus the null space of L. So we have this representation, and now we know also that NL, it's a closed linear subspace of X. We proved that. And since it's a closed linear subspace, we can define the orthogonal of this space, and this space is also a closed linear subspace, and moreover, X can also be represented by NL perp plus NL. My claim, and what I want to prove, is that this space NL perp has dimension 1. Or more precisely, that NL perp it's equal to the span of some point, let me call it Z. So what I claim is that first, N perp L is different from 0. Because, well, if it were equal to 0, that would mean that NL is equal to X, and if NL is equal to X, this means that L is equal to 0, but I'm starting here from L different from 0. So the perpendicular of L cannot be equal to 0, because if it were, that would mean that NL is X, and NL to X implies that L is equal to 0, and we know that L is different from 0. So there exists at least one element, and let me call it Z, different from 0, which belongs to n L perp. Now I claim that, well, the dimension is 1, which means that I can't have 2 points in this set which are linearly independent. So let's assume that we have 2 points, Z1 and Z2 in n L perp. And I want to show that they can't be linearly independent. Well, since Z1 it's an element of X, it can be written by this identity as alpha 1 times W plus N1, where N1 is an element of the null space. And the same thing for Z2. So let's assume that these points are different from 0. This means that alpha 1 cannot be equal to 0. Because if alpha 1 is equal to 0, that would mean that Z1 is equal to N1, which is an element of the null space. On the other hand, Z it's an element of the orthogonal space. If Z is an element of the space and of its orthogonal, this means that Z is equal to 0. Therefore, alpha 1 can't be 0. Let me repeat that. By the first line, the first identity, I can always write Z1 as a scalar times W plus N1. And I'm claiming that alpha 1 is different from 0. Why is that? Because if alpha 1 is equal to 0, I get that Z1 it's an element of the null space, and L. But I assume that Z1 is an element of the orthogonal, and the only element which belongs at the same time to the null space and to its orthogonal is 0. So that would lead to the identity that Z1 is 0, but I assumed that Z1 is different from 0. So I know in this decomposition that alpha 1 is different from 0, and the same thing for alpha 2. Alpha 2 has to be different from 0. Now, if I multiply the first identity by alpha 2, and the second identity by alpha 1, I get these identities. Now, subtracting these identities, I deduce that alpha 2 Z2 minus alpha 1 Z2, alpha 2 Z1, sorry, minus alpha 1 Z2, that this is equal, well, this expression will cancel to that one, that this is alpha 2 and 1 minus alpha 1 and 2. And from this I get, since Z1 and Z2 are elements of the orthogonal space, on the left-hand side I have an element of the orthogonal space, and on the right-hand side I have an element of the null space. Therefore, and since the only element which at the same time belong to the orthogonal space and to the space is 0, we have that both sides are equal to 0, and from that I conclude that alpha 2 Z1 is equal to alpha 1 Z2, and therefore that Z1, because alpha 2 is different from 0, it's equal to alpha 1 alpha 2 Z2, and therefore that I can't find two different elements of the orthogonal set which are linearly independent. Any two elements, one can be written as a scalar times the second, which proves that indeed this space has dimension 1 as I claimed. So I proved that this perpendicular space is exactly equal to, so there exists a z in X different from 0, and that this space coincides with that space. Now, let me define M as a bounded linear functional, which at X gives you X times Z. So the null space of M is all points X which are orthogonal to Z, and this is exactly N orthogonal to Z which means that the orthogonal to this space. But this space, so let me maybe write that again. So the orthogonal, the null space of M is the space of all x which are orthogonal to Z. But the space which are orthogonal to Z is the orthogonal to this space, which means it's the orthogonal of NL. Right? So what I claim is that NM is actually, so this is the space alpha Z, and NM is the orthogonal to that. Right? So let me repeat this. I define this linear functional M. Now, what is the null space of X, of this M? These are all points which are orthogonal to Z. So all points which are orthogonal to this set. So the orthogonal to this set, the perp of this set, but this set is this one, so it's the perp of this one, so it's the double perp. And we have seen that if you take, since NL it's a closed linear space, if you take the double perp, you get the original space, and therefore we proved that NM is equal to NL. And by the second lemma, or last assertion I proved, this shows that M is equal to a constant time L. Therefore, or maybe let me write in the other way, that L is C times N. Therefore, L of X, it's equal to constant of Mx, but Mx by definition, it's Xz, and therefore we proved that indeed we have an element which is the complex conjugate of C times Z, such that for any x, L of x, it's given by the scalar product of this element with x, and that completes the proof of the Ris Representation Theorem. So I'll complete this lecture with a theorem which is due to Lax and Milgram, and which reads as follows. So you have X, a Hilbert space, and let's say that you have a functional B from X times X to R, or to K, and such that, well, B will be linear on the first coordinate and sesquilinear in the second coordinate, so that for any x, if you fix the second coordinate as a function of the first one, this is linear. And so if now we fix the first coordinate as a function of the second coordinate, this is sesquilinear. Which means I recall that x alpha y1 plus y2 it's equal to the complex conjugate of alpha times bxy1 plus bxy2. And this, of course, it's for all x, y1, y2 in x and alpha in k. Then we will require that B is bounded, so that bxy, the absolute value of bxy, it's bounded by a constant c1 times the norm of x, the norm of y. So this means that there exists a constant c1 such that for all x and y in x, we have that bound. And finally, there exists a second constant, which I will call C0, which is strictly positive, such that for all x in x, bx, x, it's bounded below by C0 x squared. So I'm assuming these three assumptions on B, and the statement says that, well, then for all L, so for all bounded linear functional L, there exist x in x such that L of y is equal to byx for all y in x. So we have a representation of bounded linear functions L in terms of this, I would say, bilinear functional B, but understanding that on the second coordinate it's not linear, but sesquilinear. So this is, in some sense, an extension of Ris Representation Theorem. Now we have this B, which plays the role of a scalar product, satisfying these. So these are, the first assumption are exactly the assumption of the scalar product, and then we have, besides these two conditions, and under these two extra conditions, we can represent any bounded linear functional in terms of this functional B. So this is the last theorem of this lecture, which I will now prove. So proof. Well, we know that so if I fix the second coordinate as a function of the first coordinate, this is a linear functional, and it's a bounded linear functional. So this is a bounded linear functional. And it's bounded because we know that byx, by the second property of B, so that this is bounded by C1, norm of x, norm of y. So x is fixed, so this is a constant, and therefore, as a function of y, this is bounded by a constant times the norm of y. Therefore, B, as a function of the first coordinate, it's a bounded linear functional. So this tells me, by the Ris Representation Theorem, that there exists an element which I will represent by Tx. So this is an element of x, such that byx, it's equal to the scalar product of y with t of x. Right? So Ris Representation Theorem tells me that for that fixed x, this linear functional can be represented by this scalar product. So my first claim is that, well, this functional, so t, which is a functional from x to x, for each x gives me a new vector in x, well, it is linear. So I want to show that t alpha x1 plus x2, it's equal to alpha t of x1 plus t of x2. And this is more or less obvious. So by definition, we have that by alpha x1 plus x2, that this is equal to, by definition of t, this is y t of alpha x1 plus x2. Right? So we know that there exists an element in x, which I'm calling t of alpha x1 plus x2, such that this bounded linear functional is represented by this scalar product. On the other hand, using the fact that B is sesquilinear on the second coordinate, this is equal to the complex conjugate of alpha times B of y x1 plus B of y x2. Now, by definition of t, this is equal to alpha complex conjugate y t of x1 plus y t of x2. And now by the sesquilinearity of the scalar product, this is equal to y t of alpha tx1 plus tx2. And so what we get is that for all y in x, y t alpha x1 plus x2 is equal to y t of alpha t x1 plus tx2. And I claim that this implies that t of alpha x1 plus x2 it's equal to t alpha t of x1 plus tx2. And that's clear. So maybe let me prove that. So we have that alpha z1 it's equal to y z2 for all y. So this implies that y z1 minus z2 it's equal to 0 for all y. Take y equal to z1 minus z2. From this we get that z1 minus z2 norm square it's equal to 0, and this implies that z1 it's equal to z2. So this is what I'm using to conclude here that t of alpha x1 plus x2 it's equal to alpha tx1 plus t of x2, and therefore that t is linear as I claimed. So now let me call A the image of t. So this is the set of all tx such that x is in x. And what I claim, so here I just recall that we proved already that t is linear. So what I claim is that t, A, is a closed linear subspace of x. So we, by the linearity of t, we know that this space is linear, right? If I take y1, y2 in A and alpha in K, I want to prove that alpha y1 plus y2 belongs to K. But since y1 belongs to A and y2 belongs to A, this means that there exist x1 and x2 such that t of x1 is y1, t of x2 is y2. Now, if I take t of alpha x1 plus x2, by linearity of t, this is alpha tx1 plus t of x2, which is alpha y1 plus y2. This is an element of A because it's the image of alpha x1 plus x2 by t, and therefore alpha y1 plus y2 belongs to A, and that proves that A is a linear subspace of x. Now I want to show that this linear subspace is closed. So let me take, so maybe let me erase because I will need some space. So now I'm considering y, the sequence yn in A, and I'm assuming that yn converge to some y. And I want to show that y belongs to A. Well, what I claim is that there exist C2 and C3 such that C2 times the norm of x square, it's bounded by tx square, which is bounded by C2 the norm of x squared. And here t of x, tx means that t of x. So I want to prove this bound in order to get that the set A is closed. And this will follow from this identity. So I have that B yx, it's equal to y tx, and this for all y. So if I take y equal to x, what I get is that bxx, it's equal to x t of x, and this by Schwarz inequality, it's bounded by the norm of x and times the norm of t of x. On the other hand, we know that bxx, it's bounded below by c0 x squared. This is one of the assumptions on B. And from this inequality, we get that c0 times the norm of x, it's bounded by tx. So it's this inequality where c2 will be just c0 squared. So we proved that inequality. Now, if you want to prove the other inequality, let's take y equal to t of x in this identity. And now what we know, what we have, is that t of x squared, which is the right-hand side, that this is equal to b t of x x. And, well, we have seen that the absolute value of b tx x, it's bounded by c1, the norm of tx, the norm of x. And from this, we get, dividing by t of x, that the norm of tx, it's bounded by c1 times the norm of x, which is the second inequality which I claimed. So from that, so we proved these two inequalities, and we have now everything we need in order to prove that A is closed. So let's assume that yn converges to y. So since yn belongs to A, this means that yn is equal to txn. Now yn it's converging, so this means that yn is Cauchy. But since yn is t of xn, so we get that t of xn it's a Cauchy sequence, and from this inequality, it turns out that xn is Cauchy. So from this, we get that xn is Cauchy. Since we are working on a Hilbert space, this space is complete. So this means that xn it's converging to x. And now I claim that yn it's converging to t of x. Well, but yn minus t of x, this is equal, yn it's t of xn. T is linear. And now we can use the second inequality that, well, t of xn minus x, it's bounded by a constant, the norm, it's bounded by a constant times the norm of x. So this is smaller than the constant times the norm of xn minus x. But xn is converging to x, therefore this is converging to 0, and from that we get that yn is actually converging to t of x. So we have the same sequence, yn, which is converging to y by assumption, and we proved that yn is also converging to t of x. And from the uniqueness of limits, we get that y is equal to t of x, which means that this implies that y is equal to t of x, and therefore that y belongs to A, because y is in the image of t. And therefore, we proved that this space is a closed linear subspace of X. So now we have that A. So we proved that A, which is this space, is a closed linear subspace. So now my claim is that actually A is equal to X. And well, to prove that A is equal to X, assume that A is different from X. So since X can be written as A plus the orthogonal to A, this means that there exists an element Z in X, which belongs to the orthogonal of A. Therefore, Z is orthogonal to all elements of A, so Zy is equal to 0 for all y in A. So if A is different from X, we can find an element Z in X, which is orthogonal to all elements of A. So Zy, so for all y in A, Zy it's equal to 0. So 0 it's equal to Zy. But since y is an element of A, this means that Z, y is some tx. So there exists x in X. So actually, all elements of A are represented as tx. So we have that Z tx is equal to 0 for all x in X, because these are the elements of A. But now, by the representation of B in terms of the scalar product, this means that B of Zx is equal to 0 for all x in X. So take x equal to Z. From that we have that Bxx it's equal to 0. But remember, I'm sorry, let me write that as ZZ instead of XX, because, well, x is equal to Z, so I'm choosing here x to be Z. So I get that BZZ is 0. But if you remember, one of the assumptions is that BZZ is bounded below by C0, the norm of Z squared. And therefore, we get that the norm of Z is equal to 0. And this proves that the unique element of A orthogonal is the element 0. So either it's a contradiction or it's a proof that A orthogonal is reduced to the element 0. And that proves that A is equal to X. So A is the set, the image of T, which is defined over there. We proved that actually this image is equal to X. Now we can complete the proof. Let L be a bounded linear functional. Well, by Ris Representation Theorem, there exists some y in X such that L of Z is equal to Zy for all Z in X. So this is Ris Representation Theorem, which tells us that all bounded linear functional can be expressed in terms of the scalar product. But now we know that the image of X by T is the whole set. So there exists, by this result, X in X such that t of x is equal to y. So this means that L of z is equal to z of tx. And by this identity, by definition of t, this is equal to b zx. So we just proved that whatever L bounded linear functional, we can find an x in x such that L of z is equal to b zx for all z in x, and that completes this lecture.